So continuing our study of double or half angle formulas, here are some new ones. Okay, so why would sine squared theta be 1 minus cos 2 theta over 2? So remember, we had the cosine of 2 theta is 1 minus 2 sine squared theta. This was one of our double angle formulas for cosine. Now if I add 2 sine theta to this side and subtract cos of 2 theta to that side, we end up with 2 sine squared theta equals 1 minus cosine of 2 theta. And if I divide by 2, we get right here. Okay? So that's all there is to that. However, we also had a double angle formula for cosine that said the cosine of 2 theta is 2 cos squared theta minus 1. Add 1 to both sides and divide by 2, and you get exactly here. Okay, and then you can get the version for tangent just by using the ratio of sine squared over cos squared. So tangent squared is sine squared theta over cos squared theta. And now we have this formula for sine squared. It's 1 minus the cosine of 2 theta over 2 over cos squared, which is 1 plus cosine of 2 theta over 2. And those shared denominators of 2 cancel, and you get exactly formula 8 here. So again, these are not really new formulas. They're just using the formulas we already had and playing them off one another. So everything in this section really came from the sum formulas for sine and cosine. But here we have them. Okay, we have a sine squared equals, a cos squared equals, and a tan squared equals. So can we write an expression for cosine to the fourth that doesn't involve any powers greater than 1? All we really need to do is write this as cos squared of theta squared. Okay, so cos squared of theta can be written in a couple different ways, but one is 1 plus cosine of 2 theta over 2, and then I'm going to square that. So notice what happens is our goal was to get the powers of sine and cosine have to just be 1. Now when I square that fraction, we do get a 1/4, which we factor out just so we don't have to worry about it. But when I FOIL that numerator, okay, we get a 1. We get a cosine of 2 theta, which meets our requirements. The power on that cosine is only 1. But we do get a cos squared of 2 theta. So now what we have to do is we have to use the formula cos squared of theta is equal to, say, 1 plus cos of 2 theta over 2. Okay, this is just one of our double angle formulas for cosine. But now notice we don't have cos squared of theta, we have cos squared of 2 theta. Now the only real important relationship is that cos squared of angle, whatever that angle is 1 plus the cosine of 2 times that angle over 2. So if that angle is theta, great, we have the formula here. But now in this line at the far right side of the screen, the angle is not theta, the angle is 2 theta. So if I apply this formula, okay, what we end up with is, okay, they just distribute the fourth. So how do I deal with that cos squared of 2 theta? We're just going to apply the double angle formula again, 1 plus the cosine of twice that angle. The angle now is 2 theta, so twice it is going to be 4 theta. And you could distribute this out, maybe give it a common denominator if you want, totally optional. Once you distribute the 1/8, I guess one simplification that the book considers worth doing is saying 1/8 plus a quarter is 3/8. Sure, why not? Okay. Can we find all angles between 0 and 2 pi so that the sine of theta times the cosine of theta is -1/4? And remember, this doesn't mean, for example, that one of them is a half and one of them is minus a half. It just means their product is -1/4, and there are lots of ways that could happen. So there are actually a good quantity of techniques we could use to solve this. But one way would be to recognize that the left-hand side really looks like the double angle formula for sine. It's just missing a factor of 2. So if I multiply both sides by 2, okay, we end up with 2 sine theta cos theta is -1/2. But then that left-hand side is just the sine of 2 theta. So now I have the sine of 2 theta is -1/2. And now it's a chapter 6 problem. Find all angles from 0 to 2 pi so that the sine of 2 theta is -1/2. Actually, I think that was chapter 7. It was just earlier. I'm losing track. But this is definitely a problem we've done before. Okay. So 2 theta is the argument. So the equation we're trying to solve now is that the sine of 2 theta is equal to -1/2. Okay, here's what we're trying to solve, where theta goes between 0 and 2 pi. Okay, so the angles for which the sine is -1/2 would be, say, 11 pi over 6 plus any even quantity of pi's. Okay, it's not the only solution, but we go ahead and solve that. But notice that that angle is now 2 theta, not theta. So we divide out that 2, and we get the following. And we're interested in thetas between 0 and 2 pi, which means we can let that number k, where is it, k, either be 0 or 1. Okay, if k is -1, we end up with a negative angle. That's too small. If k is 0, we are in between 0 and 2 pi. If k is 1, we're in between 0 and 2 pi. But if k is 2, we are too large. So this was for the solution 11 pi over 6. But 7 pi over 6 is also a solution for an angle so that the sine of that angle is -1/2. But again, we can take any integer k. There's a little typo. There should be a k here. So now what we need to do is let 2 theta, the actual argument of the sine function in this problem, be that solution, and ask which values of k give me solutions in between 0 and 2 pi. Well, oh, sorry, first we should divide out that 2, of course, turning 7 pi over 6 plus 2 pi k into just 7 pi over 12 plus pi k. Well, k equals -1 gives me a negative result. That doesn't count. K equals 0. That's in between 0 and 2 pi. K equals 1 is also in between 0 and 2 pi. But k equals 2 is too large. That's larger than 2 pi. So overall, we found 4 solutions, and there they were. Okay, once we hit the point, the only real new step in this problem, so let's just remember, we started off with this. The only new step was to say, if I just multiply this by 2, now I can call this the sine of 2 theta. And as soon as we hit this point, this is a problem we've already learned how to solve. So the half angle formula was really only the first step in here, and after that it became something else. And just, realize that problems given on exams or in homework, frequently that's the sort of pattern. You'll use material from one section, and then you'll have a problem that was from another section, so we can combine different approaches in the same problem. You shouldn't expect a midterm or final exam problem to just have like one step and you just have to do that and that's fine. That's the sort of thing we assign on homework right when you learn that material so that you can practice the new thing right away. But by the time exams roll around, you need to be able to synthesize different sections into the same problem. Another example. So projectile motion is where an object is given some sort of initial direction and velocity, and after that it just follows its own inertia and acted on by gravity. And we ignore air resistance because it makes it a lot harder. So ignoring air resistance, okay, if we fire something at an angle of theta, so that's this upward firing angle, with a velocity of v sub 0, so this is the initial speed that it comes out of the cannon. Ignoring air resistance, the final range r, the actual distance the object travels before hitting the ground, is given by the following function. Okay, 1/16 times the initial velocity squared times the sine of the angle times the cosine of the angle. So step A, show that if you didn't want to use both sine and cosine, you could use this formula here, 1/32 times the velocity squared times the sine of 2 theta, and then use that formula to find an angle so that the range is maximized. Now, many of you may intuitively know if you want to launch something that you pick an angle that's like an even split, it's 45 degrees. But let's see why it is, assuming that this initial formula is accurate, okay, which it is. And if you take, I'm trying to remember exactly what course you can do this formula in. It's either Calc 1 or Calc 3. But I don't exactly remember. But in any case, let's get through it. Let's get to part A. Well, part A, notice we're trying to get a new formula that's almost exactly the same. It's just instead of a sine theta cos theta, we want a sine of 2 theta. So we're really just going to do the same thing we did in the previous example. Where we have sine theta cos theta, okay, I'm just going to multiply and divide by 2, but now I have 2 sine theta cos theta, which I can replace with the sine of 2 theta. And now that extra 2 in the denominator made the fraction out in front 1/32 instead of 1/16. Okay, so this part A was pretty straightforward. It's just replace sine theta cos theta, multiply and divide by 2 so that you can use a half angle formula, or a double angle formula, sorry. on this right here. Okay, so now we have a new formula, and now the question is, how do I make this as large as possible? Now, we're assuming that the speed v can't be changed. It's just like the initial, it's how fast something comes out of your cannon or your launcher or whatever, and due to the design of the object, that's not going to change. What you can change is the angle. Okay, and we just found that the range, I'll copy it, is 1 over 32. Well, I can't change that. The initial velocity squared, well, I can't change that, times the sine of 2 theta. Well, I can change the angle. So how do I make the sine of something as large as possible? The biggest the sine value can ever get is 1, which means what I want to plug in is 90 degrees, or pi over 2 radians. That will tell me that I can get out 1. So either 90 degrees or pi over 2 radians, but notice that's 2 theta, which means once I divide by 2, I want the angle to be 45 degrees. So indeed, the angle that gets my object the furthest distance is 45 degrees. Okay. Let me erase my work, because the same work is now going to show up in nice computer text. So yes, 45-degree angle gets the largest range. Now you could imagine, here's my cannon, okay, and I can fire my object. Let's suppose here's my maximum range. There's a target here, so it's within the maximum range. What angle do I want to point my cannon at? I have two options. Okay, if I point it in shallow, I can get a trajectory like this, but if I point it especially steep, I can get a trajectory like this. And which one is preferred really depends on the specifics of your application. Like if I'm firing my Super Soaker water gun, I'm probably going to go with the shallow trajectory, because a stream of water, if you give it lots of time, is going to break up and change into just a gentle stream. However, if I have some sort of like large artillery shell, the shallow trajectory runs the risk of it actually bouncing on the ground. So old-style cannonballs, like if you read accounts of like Napoleonic Wars, cannonballs, when they are fired shallow, they really bounce off the ground and roll around and can be very deadly. It honestly means you don't actually have to hit your target. You just have to hit in front of them, and it will just bounce its way along. But if you don't want that to happen, you might choose a steeper trajectory so that the projectile comes down at a steeper angle and is less likely to bounce around. Anyway, that's going to close out this video in here. So come on back when we will continue our study of half angle and double angle identities. Now, all the ones we've done so far involve replacing a theta with a 2 theta. They're called double angle identities. The next video, we're going to learn half angle identities, where you get to replace angles alpha. I don't know why they went with alpha instead of theta, but you replace alpha with alpha over 2. So that will be the next video.